Hello, class. Earlier, we have seen Black-Scholes-Merton formula for calls and puts where the underlying stock pays no dividend. Now, we can relax that restriction. Now we're looking at stocks that are paying dividends. So suppose the stock is paying a dividend at the rate of Q continuously, then the call and the put formula under the Black-Scholes-Merton framework will be adjusted with, instead of S naught, we'll have S naught times e to the power minus qt. Same thing here for the put, and also for D1 and D2, you have a minus q terms here as well. Now let's see why that is the case. So we will derive this in two ways, which actually are consistent among those two. So the first one is, let's take a look at how we can make a intuitive adjustment to see that if the stock was to pay a dividend at the a continuous rate of Q, why we should have those terms here. And then we will rederive our fundamental partial differential equation, allowing the stock to pay a dividend yield and see how the fundamental PDE what kind of a new form the fundamental PDE will take. And by solving that, then under the new form, we will actually naturally have this being the solution. Okay, so the two are consistent. Now, if you think about it, if stock is paying dividend, and for all the dividends paid before maturity of the option, in this case, before the maturity of a call, for example, whenever a dividend is paid, the value of the stock is actually dropped by the same amount that dividend is being paid out. So, at maturity, compared to a stock that does not pay dividend, a stock that does pay dividend will not grow as much, right? So the growth rate is actually reduced by the amount of dividend or by the present value of the dividend that the stock is paying out. Because for a call, you have to have at maturity S minus K, but that S is smaller than otherwise. So if you have dividend payment, the S will be smaller compared with no dividend payment. So you should account for that. So the way to account for that is that, instead of having S naught being the price that you put in your formula, you will say, well, okay, I really don't have the full S now, because you can think about that S price has two components. One component is, just the pure dividend, present value of the dividend, where that is not going to be relevant for the call price, because that's going to be paid out before the maturity. And there's another portion of S, which, after taking out the dividend, this part is going to grow at the risk-free rate. So that portion will be relevant. So basically, that analysis lets us to think that we should replace S naught by S naught minus the present value of the dividend. So everything under the blue bracket here is the present value of the dividend. So if you sort it out, the new S is really S naught times e to the power minus qt. So if you have that, you should have everywhere in the old formula there, that has S naught, you should replace that by S naught times e to the power minus qt. Okay, so you replace that in the call price here, but you also should replace them in D1 and D2. Whenever you see an S naught, it becomes S naught times e to the power minus qt. Now, if you do that for this part, because you have a log here, log e to the power something would just be minus qt. So you can bring this out of this and minus qt here. So instead of r plus this thing times t, you have r minus q times t. Same thing for D2. So your new formula now is, compared to the old formula, you have to change your S here, and you have this form. So where you have a minus Q here. All right. So similar thing will happen to a put. Okay. Now, what if it's not, the stock is not paying dividend with the continuous dividend rate? That is basically a more idealized way of modeling something. In reality, a stock will pay out dividend periodically for a particular amount. Then you really have D1, D2, and so on, all the way to Dn. If you have n times of dividend payment prior to maturity of the option. Now, in this case, the same analogy analysis actually will apply. Then in this case, your new S naught is really, S naught minus the sum of the present value of those dividends. So by doing so, if you were to replace all the S naught by this new value, S naught star, you will then be able to calculate. You can use your old Black-Scholes formula. As long as you make that replacement, that formula will become a formula where you can use to calculate the call or the put value when the underlying stock actually pays dividend. Now let's take a look at how we can adjust the analysis related to deriving the fundamental PDE by taking into consideration of the dividend payment. In this case, let's first of all look at the situation where the stock pays a continuous dividend yield at Q, a rate of Q. So again, the process is very similar. So you have this stock process, and you will form a portfolio of delta unit, DFDS, delta unit of shares, and you will short 1 unit of derivative. Now, that portfolio, the same portfolio that we have constructed earlier, but that portfolio, instead of having one change, you actually have two sources of changes. One is the portfolio itself will receive dividend payment continuously, right? So you have delta unit of S, and for this, you're receiving dividend at the rate of Q. So Q times this is the amount of dividend that we're gonna receive per period of time. Also, the portfolio has a component of change that is exactly the same as before, right? It changed over time, and it's this change related to the second partial derivatives. So this essentially still take the old form, but then you have this one more source of income to the portfolio. Now, when the change of the portfolio value is the combination of both sources. So you add together. And that one is equal to R times the initial value of the portfolio times delta T. So drop out the delta T here, and rearrange your differential equation, that becomes df dt plus, instead of Rs times df ds, you have R minus Q times S times df dt, ds. Then this part is still the same. So really, essentially, the only change here for the fundamental partial differential equation is replacing R with R minus Q. So essentially what it says here is the in risk neutral, that instead of the growth rate for the stock being R, if the stock pays dividend at a continuous rate of Q, the risk-free growth rate for the stock is really R minus Q. So this is the only difference there. So then if you solve this particular PDE under the boundary condition for call or under the boundary condition for put, you will then recover the formula we have here, which should exactly be the same as the intuitive adjustment that we talked about earlier. Finally, if you have a stock that pays dividend at a continuous rate of Q, then your sensitivity will be different with such an adjustment here. So for example, for delta, instead of ND1, you will have E to the power minus QT times ND1. So you can derive all this in the same approach that we have shown earlier. It's just based on a different formula rather than the formula associated with the stock that is not paying dividends. So, for delta, you would have just taken the partial derivatives using this being the price of C. Okay, so I'm not gonna go into the actual derivation here. The process is very similar to what we have shown before, and I do encourage you to try to derive those ones, so that just to demonstrate or to make yourself comfortable that you're able to do this.